Good evening and welcome to this video for the 2020 Level 3 Electricity and Magnetism paper for Level 2. So as I covered in my last mechanics video for the 2020 Level 2 physics papers, I actually do not have the marking schedules for these papers, so I'm just doing this based off of what I think the correct answer is. There is a possibility that I do make a mistake, and so if I do, I apologize. And if you do find any obvious mistake in this video, I do encourage you to leave a comment down below. That's greatly appreciated. Question 1, first class cabins. In a first class cabin, the seats are filled with 4 heating units, 2 for the hands and 2 for the feet. The hand units have a resistance of 6 ohms and the foot units 10 ohms. The heating unit is connected to a 28 volt supply. Show the combined resistance of the hand units is 3 ohms. Okay, so in this case, we can see that the hand units are actually connected in a parallel circuit. The reason that it's connected in parallel is because at the junction, which is talking about the junction as in this point here, when current, actually no, conventional current flows the other way. Okay, so current flows this way. And when it gets to this junction, current can either go here, which is I1, and current can either flow here, which would be I2. Because current can flow in 2 different pathways, it's going to be a parallel circuit. So therefore, our formula we're going to be using is 1 over R total is equal to 1 over R1 plus 1 over R2. Therefore, 1 over R total equals to 1 over 6 plus 1 over 6. Therefore, 1 over R total equals to 2 over 6. Therefore, R total equals to 6 over 2, because you take the inverse and you should get the resistance is 3.0 ohms. That's our final answer. That should just be an achieve level question. So calculate the current flowing through the ammeter. Okay, so the current through the ammeter, as you can see, the ammeter is located in between the 2 parallel branches. And this means that the ammeter is actually measuring the total current. And that's because at point A, you see I1 will flow here, I1 will be here, and I2 will locate here. And at this junction, we're going to get back to I1 plus I2, which will get back to our original current, which is I total. As we can see here, the I total, the total current in the circuit, will flow through the ammeter. So basically, what this question is asking us is to find the total current in the circuit. And we know that the total current in the circuit is equal to the total supply voltage is equal to the total current in the circuit times the total resistance in the circuit. So the total resistance in the circuit is the resistance of the hand units plus the resistance of the foot units. We found the combined resistance of the hand units is 3 ohms, and we're going to do the exact same thing to find the resistance of the foot units by using the exact same formula. So you can say that 1 over RT equals to 1 over R1 plus 1 over R2, and you can label this as for the foot units. Alright, and you can say that 1 over RT equals to 1 over 10 plus 1 over 10. This equals to 2 over 10. So therefore RT equals to the inverse, which is 10 over 2. That equals to 5 ohms. And as we can see here, the foot units is actually connected to the hand units via a series circuit, okay? There's only one way the current can flow between the two. There's only one way the current can flow between the 2 arrangements. So therefore, we're going to be using the R total equals to R1 plus R2. Therefore, the total resistance in the circuit is equal to 3 plus 5, which is 8 ohms. And we can say that V equals to IR, our total voltage or supply voltage, equals to the total current times the total resistance. Therefore, the total supply voltage is 28. So 28 equals to 8 times our total current. And if we divide both sides by 8, we'll get the answer. So dividing both sides by 8, we should get 28 over 8, which is 3.5. So we should get our total current is 3.5 amps. And that's our final answer. And this should be a merit question in my opinion, okay? Looks like it's a merit level question. Question C, one of the foot units stops working. Explain what effect this will have on the current for the single hand unit. Okay, so when one of the foot units stops working, we're going to assume that stops working means that current can no longer flow through the foot unit or the bottom foot unit. That means the top foot unit is now connected to the circuit in a series arrangement. It's no longer in parallel with the broken foot unit. Therefore, the resistance of the foot units, the combined resistance of the foot units is actually going to increase because it's no longer connected in a parallel circuit, it's connected in a series circuit. So now in the series circuit is going to be equal to 10 ohms instead of the 5 ohms. So therefore, as the hand units have not changed, but the foot units has increased in resistance, the total resistance will increase. And since the supply voltage stays the same, this means that the total current in the circuit will decrease. And if the total current in the circuit will decrease, Therefore, the current at a certain junction, at this junction here, the total current will decrease. Therefore, the current I1 or I2 will also decrease. So therefore, the conclusion is that the current for a single hand unit will decrease. So if we write this one out, we can say that when the foot unit, okay, so foot unit, we're just going to abbreviate to FU, and then when the foot unit stops working, okay, current can no longer flow through the foot unit. Okay, so there is only one path way for the current to flow through the top foot unit. So hence the foot unit, so the top foot unit is connected to the circuit in series. Connected in the circuit as series. So you can actually give a reason for why the resistance increases, because we know that when we add parallel circuits, we're adding an extra pathway for the current to flow, and because we're adding an extra pathway for the current to flow, the actual resistance against that current is actually going to decrease. So therefore, in the parallel arrangement, it's always going to have a lower resistance. So we can say as parallel arrangements give more pathways for current to flow. Hence decreasing R. Alright, so you can say the total resistance has increased. So the total current has increased. Okay, so the total resistance has increased, and then we can say that because the supply voltage stays the same, because supply voltage stays constant, V equals to IR, so you can say that I is inversely proportional to R, so I decreases, and you can say hence the current through the hand unit decreases. Hence I through hand unit decreases. Sorry, I ran out of space a little bit, it's okay. So hence the current through the hand unit will decrease. So that should just be another merit level question, okay? So D, as an upgrade, the airline adds an additional heating unit labeled R to the seat. When the new heating unit is added, the power output from the supply is 120 watts. What is the value of the resistance R of the new heating unit? So when 120 watts is delivered to the external circuit, we know that P equals to IV, and we know that the source voltage is 28 volts. So using this, we can actually find the current drawn from the battery. There's a certain current drawn from the battery, and this current is going to deliver some power to the external supply, okay? So therefore, 120 equals to 21 times of this current, so 120 divided by 28. That will give us the current is equal to 4.29 amps. So that's the total current in the circuit, okay? So in this case, we can actually use V total equals to R total multiplied by I total. And in this case, we actually know our total source voltage. We don't know the total resistance, what we're trying to find. So we don't know R total, so that's what we're trying to find. And we know the I total, which we just found, was 4.29 amps, okay? So using this, we need to find our R total. All right, so we added a new resistance in the foot units as a parallel circuit, okay? So we can use our parallel circuit for resistance. So 1 over RT equals to 1 over R1 plus 1 over R2 plus 1 over R3. Because now we have three items of resistance connected in a parallel circuit. So 1 over the total resistance equals to 1 over 10 plus 1 over 10 plus 1 over R. And we just say 1 over RT equals to 2 over 10 plus 1 over R. Plus 1 over R. And using some algebra, we can actually join this up to make it one fraction. So 1 over RT equals to, so in this case, we're going to cross multiply. So we have 2 times of R over 10R and we're going to add 10. So add 10 times 1, which is add 10. So we should get 1 over the total resistance equals to 2R plus of 10 over 10R. Alright, so that's our one fraction. So R total equals to 10R divided by 2R plus of 10. That's our total resistance of the foot unit, and we need to consider the total resistance of the hand unit, which is still 3. So we can say the resistance of the hand unit, that is still 3 ohms. Right, so to find the total resistance in a circuit, we can use the total current and the supply voltage. So we know the supply voltage is 28 volts, and that equals to the I total, which we know is 4.29, multiplied by the R total. And we can rearrange and divide by 4.29 on both sides to find the R total. And we should find the R total is equal to, we write it as a fraction, it might be easier, so 98 over 15 ohms. So therefore, we can actually write our equation for our R total. We know that the total resistance is equal to the resistance of this parallel circuit plus the resistance of this parallel circuit, okay? So therefore, 98 over 15 equals to 3 plus of 10R over 2R plus of 10. So 98 over 15 minus 3. So therefore, we can say that 53 over 15 equals to 10R over 2R plus 10. We're going to cross multiply again, so therefore 53 over 2R plus 10 equals to 150R. So 53 times 2 is 106, so 106R plus 530 equals to 150R. If we subtract 106R from both sides, we should get that 44R. So 530 equals to 44R. And if we divide 530 by 44, that should give us our resistance is equal to 12.05 ohms, or approximately 12 ohms. Approximately 12 ohms. Alright, so just let me double check this one. So 1 over this plus 1, 10. One of answer plus we should get times. Alright, that seems to be the correct answer. So our correct answer here should be that the total, not total resistance, that our missing resistance R is 12 ohms. And that should be an excellence level question. Okay, pretty challenging excellence question if I say so myself. But the correct answer should be 12 ohms should be the resistance R. Question 2, lightning. Mass of the electron, they give you as 9.11 times 10 to the power of negative 31 kilograms. Charge on the electron is 1.6 times 10 to the power of negative 19 coulombs. Lightning is typically caused by a buildup of electrons in the clouds being released to Earth. The bottom of the cloud is negatively charged, and the ground under the cloud becomes positively charged. The cloud and the ground can be modeled by a pair of parallel plates. So because it says that the cloud and the ground can be modeled by parallel plates, we know that this is going to be testing us on the uniform electric field, which means that the electric force experienced anywhere in this electric field will be constant. The voltage difference between a particular cloud and the ground is 1.75 times 10 to the power of 8 volts, and the electric field strength is 8.57 times 10 to the power of 4 volts per meter. Find the height of the find the height of the cloud above the ground. So in this case, they're giving you an unfamiliar situation, but they're just trying to test your understanding of a uniform electric field. So find the height of the cloud above the ground. That's basically just asking us for the distance of separation between the two modeled parallel plates. So they're just asking us for this distance here. And they didn't ask us to draw the field lines, but we can draw the field lines. It's going from positive to negative, and it should be evenly spaced out. Okay, I'm just going to do a rough sketch, but should be evenly spaced out, and the electric field lines should be straight, and there should be curved electric field lines to represent a weaker electric field at around the base. So that's what it will look like if we made us draw the electric field lines. But let's just get to the question. So find the height of the cloud above the ground. So we can use that E equals to V over D. And we know that E is 8.57 times 10 to the power of 4. That equals to the the potential difference, which is 1.75 times 10 to the power of 8 over D. So therefore, D equals to 1.75 times 10 to the power of 8 divided by 8.57 times 10 to the power of 4. Alright. Times 10 to the power of 8. 8.57 Alright, so that's pretty nice number. So we should have D equals to 2042 meters. Okay, that's seems reasonable answer. So D is 2042 meters. You can round this one down to 2040 meters. Doesn't really matter. In level 2, they don't really test your rounding, but you can round it if you want. Question B. A weather balloon is released from the ground. The balloon has a charge of 3.7. 3.7. What was this unit? It's 10 to, times 10 to the power of negative 6 coulombs. Calculate the size and direction of the electrostatic force exerted on the balloon when it is halfway between the cloud and the ground. Okay, so the size of the electrostatic force, it would be given as F equals to EQ, and this force would be the same anywhere in this electric field since it's a uniform electric field, and that means that the electric force experienced by anything with charge in this electric field will be the same anywhere between these two plates. Well, it's not actually the two plates, but it's actually, in this scenario, it's between the ground and the cloud. So any item with charge between the cloud and the ground will have experiencing the same electric field force, okay, because it's a uniform electric field. So F equals to EQ, and we can calculate the size using E is 8.57 times 10 to the power 4, and the charge was given to us as 3.7 times 10 to the power negative 6. And that should give us an answer of 0.13709 newtons, which can round it down to just 0.1317 newtons. And the direction of this force, because we see here that the charge of the balloon is actually positive. Okay, so this is a positive charge, and the electric field lines are pointing in the direction that a positive charge will be experiencing a force. So the positive charge will experience a force towards the negative plate. But in this case, you can't really say negative plate, since in this situation, we're talking about the cloud and the ground. So in this case, you're going to say that the weather balloon is having an electrostatic force that is attracting it towards the negatively charged cloud. So in this case, the positively charged balloon experiences a force towards the negatively charged. Towards a negatively charged cloud. Yeah, and that should be our final answer. So this first question here should just be an achieved. The second question here, it might be a merit, but merit if you can give both size and direction, and achieved if you can give either the size or direction. Alright, so how does the electrostatic force on an electron change as it travels from the cloud to the ground? Use physics principles to explain your answer. So as I was just saying, this is a uniform electric field, which means that the force experienced at any place between the cloud and the ground will be the same. Since the charge on the the charge on the balloon doesn't change, not the balloon in this case, and the charge on the electron doesn't change, and the electric field strength is the same throughout the whole electric field. So therefore, the force experienced by this electron will be the same everywhere in the electric field. So you can say that the parallel. You can not necessarily start with that. Start with since the cloud and ground are modeled by parallel plates, it represents a uniform electric field. And you explain what that means. So when you say a uniform electric field, state what that means, meaning the electric field strength at any point, between the plates okay, so that means the electric field strength at any point between the plates is the same. So you can say, since the charge on the electron does not change, F equals to EQ, meaning that in this uniform electric field, the electric force experienced at any point will be constant. The electric force Same. So you can say, hence the force does not change as the electron travels down. Alright, so D. An electron is discharged downwards from the base of the cloud with a speed of 1.2 times 10 to the power of 5 meters per second. It reaches a speed of 4.2 times 10 to the power of 5 meters per second. Calculate the distance it could have traveled from the cloud to have reached the speed. Alright, so the electron is discharged downwards from the base of the cloud with a particular speed. So this speed comes from any particular forces that are pulling this electron down. So this actually is not a result of the potential energy lost in the electric field. So once the electron is in the electric field that's between the cloud and the ground, it's going to have an electric potential energy. And this electric potential energy is going to be converted into kinetic energy as the electron accelerates down towards the ground, which is positively charged. So once it accelerates downwards, it's going to gain kinetic energy. It's going to lose electric potential energy, and once it reaches the bottom, which is the ground, it's going to have no It's going to have no electric potential energy, and it's going to have all of its electric potential energy has been converted into kinetic energy. Alright, so in this case, okay, so we're going to find the amount of kinetic energy gained, okay? So we're not going to find the kinetic energy the electron has. We're going to find the amount of kinetic energy the electron has gained we're going to calculate what the kinetic energy the electron has gained from when it started inside the electric field to when it has reached the ground. So the change in V of the electron is equal to 4.20 times 10 to the power 5 minus 1.2 times 10 to the power 5. This equals to 3 times 10 to the power 5 meters per second. So that's the change in V, okay? So that's how much velocity it's gained while it was inside the electric field. So therefore, the EK gain, so we should make this very clear. So EK gained equals to half m change in V squared. So EK gained equals to a half times of the mass of the electron, which I gave you was 9.11 times 10 to the power of negative 31 times the 3 times 10 to the power of 5 squared. Alright, so just be careful when you're entering into the calculator. It's very easy to make mistakes when you have very big powers, so just be wary of that. 3 times 10 to the power of 5 squared times. Right, so we should get EK gained. We'll just say EKG equals to 4.0955 times 10 to the power of negative 20 joules. The kinetic energy gain comes from all of the electric potential energy. Sorry, I keep saying elastic, so let me just apologize. Okay, it comes from the electric potential energy that it started with at the top of the cloud. So in this case, EK equals to EP lost. So EP lost equals to EQD, and therefore 4.0955 times 10 to the power of negative 20, that equals to 8.57 times 10 to the power 4, that's the electric field strength, multiplied by the charge on the electron, which is 1.6 times 10 to the power of negative 19, and times the distance, which we do not know, which we're trying to find. So this divided by 8.57 times 10 to the power 4, divided by 1.6. Okay, so we should get the distance should be 2.99 times 10 to the power of negative 6 meters. Okay, so the distance is traveled in particular is 2.99 times 10 to the power of negative 6 meters. And that should be our final answer for this question. And this should be an excellence level question. And this top one should be a merit level question. Alright, so question 3, the plane. A plane of metal wings has one wingtip painted blue and the other wingtip painted red. The wingspan is 68.4 meters. The plane is flying horizontally at 850 kilometers per hour. 236 meters per second in a region where the Earth's magnetic field is vertical and has a strength of 40 times 10 to the power of negative 6 Tesla. Question A, show the voltage induced between the ends of the wings is 0.646 volts. So we know that the size of the voltage induced is equal to the size of the magnetic field times the velocity of the conductor and multiplied by the length. So in this case, we can say that the voltage induced is equal to the magnetic field strength, which is 40 times 10 to the power of negative 6. The velocity, which is 236, times the length, which is 68.4. And that indeed gives us an answer of 0.646 volts. That's just an achieve level question, a show question, just one step calculation. Complete the following table. Assume each change is made to the original plane separately. So the first change is that the speed of the plane increases. When the speed of the plane increases, we know that it's going to have a faster relative velocity in the magnetic field. Therefore, the voltage induced is going to increase as shown by V equals to BVL. So big V is proportional to the velocity. So we can say the effect is that it will increase. And which color wingtip is positive? Since the plane hasn't been inverted, it's not flying in a different direction, the magnetic field is still in the same direction, and it's traveling in the same direction. Therefore, the same color tip is positive, and in this case, it will be the red tip. And you can actually use the backhand step rule in this case. So basically, in this case, the back of your palm points towards the direction the plane is traveling in, which is right. Sorry. And your fingers point towards the direction of the magnetic field, which is into the page. And therefore, your thumb will point in the direction of the conventional current. So since your thumb is pointing in the direction of the conventional current, you should find that your thumb is pointing upwards. Because your thumb is pointing upwards, this means that current is flowing in an anti-clockwise direction. Since current is flowing in an anti-clockwise direction, this means that the top tip must be positive and then the bottom tip must be negative. This means that the force experienced by the electrons on the plane must be downwards because electrons travel from the top tip of the plane towards the bottom tip of the plane. Therefore, the blue tip becomes negatively charged and the red tip becomes positively charged. What we're left with is a positive charge here, and this becomes negative, and therefore there's a potential difference between the red tip and the blue tip, and there's going to be a voltage induced. There's a voltage induced. However, for a current to be induced, there needs to be a closed loop. So if we add like a closed loop here, voltmeter and ammeter, what am I saying? So if we add an ammeter here, there'll be a current induced since it's a closed loop. Alright, so which color wingtip is positive? That'll be red. So plane is flown in the opposite direction with the same speed. Effect on the size of the induced voltage is same because there's no change to the magnetic field strength, the velocity, or the length of the plane. Which color wingtip is positive? Okay, so I've had a couple of students argue with me about this question, saying it's very poorly worded, which I do agree. Because flown in the opposite direction, that could mean that the plane is just flying backwards with its tip facing this way, so it's just going directly backwards. And in that case, the blue tip is going to become positively charged and the red tip is going to become negatively charged. And you can use the backhand snap rule. You'll see that the thumb is pointing in the downwards direction now. Current is flowing in the if there's a closed loop, current is flowing in a clockwise direction. Therefore, the bottom tip will become positively charged. That's assuming that the plane does not turn around in a circle and just goes directly backwards. However, some students have also argued that the plane needs to turn 180 degrees in order to fly the other way. Therefore, when it does turn 180 degrees, you'll find that the blue tip will then be facing up and the red tip will be facing down. So therefore, there's actually no change. Since the red tip is facing down, that means the bottom tip will become positively charged. And therefore, it's again going to be the red tip that's going to be positive. So that's some students have argued. So I'm just going to say, if the plane is, okay, so we're just going to make another table here, if that makes anyone, if it makes a constellation. So we make another one here. So this is opposite direction at the same speed. So we say this is a turn around. And we can say this is opposite direction, no turnaround. So no turnaround. Alright, so if it's turned around, then it's still going to be red. That's going to be the positive tip. So plane climbs vertically upwards from the Earth. So for this one, some people have said this question is interesting and it's very confusing. But if you if you just read the question, you'll say that the Earth's magnetic field is vertical. Very easy to miss. The Earth's magnetic field is vertical. Therefore, into the page here is vertical. So basically, if the plane is flying vertically into the magnetic field, it's going to be parallel to the magnetic field lines. Therefore, there's actually going to be no voltage induced because there's no because it's going to be parallel to the magnetic field lines. Therefore, there's no voltage induced, and therefore the effect on the size of the induced voltage, we can say that it's 0 volts, and therefore which color wingtip is positive? So we can just say no voltage induced. We can just say nothing there. And if we say the plane doesn't turn around, it's the same induced voltage, and this will be blue. Alright, so the voltage induced is actually BVL. VL sine theta, with like sine theta is basically the angle that the plane makes with the magnetic field lines. Since we have to take the perpendicular component of the velocity when it comes to finding the induced voltage. We need to find the horizontal component of the velocity, the component of the velocity that's perpendicular to magnetic field lines. So we're going to add the sine theta. So you should see that if the plane is flying perpendicular to the magnetic field lines like it's doing now, so 90-degree angle, sine of 90 is 1. You should notice the sine of 90 is 1. Therefore, for these equations level 2, we just say V equals to BVL sine of 90, but that just equals to BVL, so we don't write the sine theta. But if we're looking at the plane flying in a parallel to the magnetic field lines, it's going to be V equals to BVL sine of 0. And therefore sine of 0 is 0, therefore there's actually no voltage induced, because there's actually no component of the velocity that is perpendicular to the magnetic field lines, therefore there's actually no voltage induced. So in this case, it's going to be no voltage induced there. Right, so inside the plane, an electric feeder wire runs under the floor of the cabin. The wire is connected to a 28 volt supply and the circuit has 5.0 ohm resistance. If the current is flowing in the direction shown in the wire, calculate the magnitude and state the direction of the force on the wire due to the Earth's magnetic field. Okay, so in this case, we can say that the magnitude of the force is F equals to BIL. F equals to BIL, that's the force on the current carrying conductor in the magnetic field. So as you can see here, a wire is a conductor and is carrying current. So that's a force on the current carrying conductor inside a magnetic field. It's going to experience a magnetic force. So in this case, F equals to BIL, and we need to find the current. We can just use our Ohm's law, which is V equals to IR. So 28 equals to 5 times of I, and you can find our current. So 28 over 5, that's current equals to 5.6 amps. Therefore, F equals to B, which is something. 40 times 10 to the power of negative 6. So F equals to 40 times 10 to the power of negative 6. Multiplied by current, which is 5.6. Multiplied by the length of the wire, which in this case they give you as 5.9. So that should give us an answer of... This equals to 1.32 times 10 to the power of negative 3 newtons. So in order to find the direction of the force on the current carrying conductor inside a magnetic field, we need to use the right-hand snap rule. So in this case, your thumb is pointing in the direction of the current, which in this case is upwards. Your fingers are pointing in the direction of the magnetic field, which is into the page. And therefore, your palm is going to be pointing in the direction of the force. So if you did the rule, so if you're doing the rule correctly right now, you should see that the palm is facing towards the left. Therefore, the wire should be experiencing a force to the left. So this makes sense since the plane is moving to the right. Okay, the plane is moving to the right. Therefore, the magnetic force experienced by the current carrying the conductor will be to the left, which makes sense because if it's also to the right, therefore the plane will just keep speeding up, and then it's just going to be a disaster for everyone. It's not going to end well. We'll just say that. So the magnetic force is in the opposite direction of the travel inside the magnetic field, which makes sense. So therefore, left should be the answer here. So once again, your thumb is pointing in the direction of the current, that's upwards. Your fingers are pointing towards the direction of the magnetic field, which is into the page. And you should find that your palm is facing towards the left. So therefore, the magnetic field on this current carrying conductor in the magnetic field is in the left direction. Alright, so an engineer designs a speed warning device that consists of a wire connecting the wingtips and a 0.5 volt lamp. The engineer states that the faster the plane goes, the brighter the lamp will glow. Use physics principles to explain and justify if and how this arrangement will work as a speed warning device. So basically how this one will work is as the plane speed increases, there's going to be a higher voltage induced in the plane because there's a higher component of, well, it's not really a component, it's just a higher velocity of the plane that's perpendicular to the magnetic field. Therefore, there's going to be an increased induced voltage. If there's an increased induced voltage and there's a lamp that's connected to a closed circuit, which we have here, so we have a wire connecting the wingtips and a 0.5 volt lamp, so that's going to be a current flowing through, there's going to be a current flowing through the lamp. And we know that the brightness of the lamp depends on the power it has, so P equals to IV. And we know that as the velocity of the plane increases, the voltage induced increases, and therefore you can see that the power increases, which means that the lamp will start to glow brighter. If the light starts to glow brighter, then therefore Therefore, if the lamp is brighter, then therefore, as it gets to a certain brightness, it can act as a speed warning device. It's like, oh, the plane is now going too fast because this bulb is now at a certain brightness. And you should see that the current should also increase, since when the voltage increases, the resistance of this bulb remains constant, which means that the current here will also increase. Okay, so the current within this mini circuit will also increase. Alright, so you can say that as the plane travels perpendicular sorry, what am I saying? It induces. Sorry, I'm just not doing. So, as a plane travels perpendicular to the magnetic field, it induces a voltage on the plane tips. The size of this voltage depends on the size of the velocity. As the velocity increases, a higher voltage is induced. Higher. This is, and you can say this is because more electrons are flowing towards the bottom tip, and therefore there's a higher potential difference because the electrons will experience more force towards the bottom tip. Therefore, there's going to be even more. The protons don't move, only the electrons experience force, and only the electrons are moving. Therefore, the proton's going to stay at the top, so the top's going to be positively charged, and the bottom's going to be more negatively charged, so therefore there's going to be a higher potential difference. We can say that a higher voltage is introduced across the tips as electrons experience force down to a red tip. So making the blue tip positive and the red tip negative. So at high velocities, there is a higher potential difference between the tips. Since there is a closed circuit, current can flow in the circuit. And that is conventional current would be the blue tip to the red tip. So blue. Yeah, and that's for conventional current. So blue tip to a red tip. Oh, they reversed it this time. Oh, I didn't realize that. They switched the directions around when I wasn't looking. Okay, so in this case, the red tip here will be positive. The blue tip here will be negative. Okay. So it would be red to blue. And that would be the blue tip. That one's towards the blue tip. Okay, so where was I? So there's a high potential difference between the tips. Since there's a closed circuit, current can flow in the circuit. And hence, as P equals to IV. And both the current and voltage across the bulb. As velocity increases, when the bulb has a certain brightness, so when the plane has a certain when the bulb has a certain brightness, it could serve as a signal for speed limit, basically, and that's really it. And that's really all you need to say for this question, and this should be an excellence level question. This is definitely an excellence level question. And for the previous question, this is a merit level question, and this is probably a merit level question as well. Alright, so thank you for watching this video. I hope you enjoyed, and I hope to see you all